Okay, thanks everyone for coming. And we have a very long agenda today. So first of all, we are going to talk about the motivations for why we are doing this. And then we are going to present our solution, an overview of that, and then dive deep into the architecture design. And then we're going to talk about integration with the Apache Spark Iceberg connector, and also integration with Iceberg REST catalog via Apache Gravitino. And in the end, we're going to talk about the next step about what we want to do. So first of all, I want to talk about the motivations of why we are interested in multi-table, multi-statement transactions for Iceberg. The motivation one is really to go beyond commit. So what Iceberg offers today is, in my summary, these four things. So all successful commits to a table forms a serializable history, and this is directly enforced in the table spec. And when multiple processes commit to the same table, well, it is guaranteed that only one wins. And this is guarded kind of by different catalog implementations using atomic features. And when a process fails to commit, it kind of retries and do this kind of rebase process and recommit if possible. This is implemented in different language SDKs that is brought into different engine integrations. And in the end, there's a feature to commit to multiple tables economically. This is a part of the Iceberg REST catalog spec, and is implemented in solutions like Apache Polaris if you want to use that. For more details, there's a talk in the morning done by Russell about transactions, isolations, Iceberg. I would recommend people to watch the video afterwards for more details. And then the next question is really think about next step. What is the next thing for a fully transactional lakehouse? In my mind, it is two different things. The first is multi-table transaction. We actually want to, just like traditional databases, be able to run begin and do different things, and then run commit, or I want to run rollback. And in the transaction block, you can actually do different DDLs, DMLs, again, any tables or any objects, right? And if we think even more advanced things in commercial products like Microsoft SQL Server, you can actually even do distributed transaction, which means you begin a transaction in one process and pass the transaction to another process to be committed. And this actually fits really well into the multi-engine world of a lakehouse. If you think about, I can do something in one engine and pass that into another engine and commit. And if you think about in Iceberg, there has been a feature called write, audit, publish. In the initial version, it is kind of designed as a staging snapshot. And in the later version, we did the branching and tagging so that you can do multiple actions to a single table and then commit a branch into the main line. And this is kind of even the next step of that, which is you can start a transaction and do whatever things inside the transaction and pass it to the auditor per se, and then commit that in the auditor process. So that is the first motivation. And the second one is we are thinking about really going beyond the Iceberg and going beyond the table concept. Because when we're thinking about this kind of multi-transaction, is it just tables? It's actually not, because the lakehouse doesn't only contain tables. It has different object types, views, MVs, policy, index, function models, all the things that all the catalog, open source, all vendor products are building. And even in the open table standards, we have today quite a few different ones, Apache Hudi, Pymon, Delta Lake, Lens, all these new formats that are specialized in different things or are used by pretty large customer base. And even not for table, but just for other things, we are seeing emerging different standards for different things, such as there's the Iceberg view spec. There are people thinking about using substrate for representing a common view, or calcite is another popular choice to do a view. And there are indexed products like Data Sketch or like Microsoft Hyperspace, all those kind of things. And in the policy space, we're also seeing people trying to use a standard policy syntax, such as Open Policy Agent, OPA, or the CEDAR policy syntax. So there are all these different standards and different object types that are emerging in a lakehouse that you probably want to transact at the same time. For example, I want to load multiple tables and then commit to, then I will refresh the MV, I will refresh my view, or set policies for different things. So they really need to work together to form a coherent experience. And the third motivation is what I call the mission towards a fully transactional lakehouse. And let me explain what that really means. And a common question that people ask me quite a lot actually is, what exactly is the isolation level for Iceberg? And there are actually many different answers depending on what you think about isolation levels. If you go to the Iceberg website and you scroll down to the end, you see this features list which directly says that serializable isolation is a feature for Iceberg, so maybe it's serializable. But if you look into the code, you will see this Java class, which gives you two isolation levels, which is serializable and snapshot. And there are documentation about what exactly that means in Iceberg. However, I think those are not really what people means when people is like a database person or like working Oracle database, MySQL, MicroSQL server. When people in those backgrounds are talking about isolation levels, it is typically these things, what I'm showing in the table. It's like read committed, read uncommitted, repeatable read, snapshot isolation, serializable isolation, and they map to different phenomena in a database system. I'm not going to all the details about these, but there's a common theme about what the isolation level means in a database in my mind. Here is a definition from ChatGPT, but it's actually quite accurate about what serializable isolation means. It is a result of executing multiple transactions concurrently is the same as if the transactions has been executed one after the other in some order, right? And if you look into snapshot isolation, it is that all reads made in a transaction will see a consistent snapshot of the database as of the time of the transaction started. So in my summary, the key thing here is that this sentence seems redundant, but the scope of the database isolation level is the entire database. If you think about serializable isolation, it is the transaction that might be spanning across different objects and have different statements. These different transactions will need to happen serially, in a logical sense. And for snapshot isolation, you are starting a snapshot, which is a snapshot of the entire database. It is not a snapshot of a single table, but the entire database has to be snapshotted and starting the transaction and then eventually being committed, right? However, the scope of the Iceberg isolation has been a single, or in the IRC commit transaction sense, it is multiple Iceberg tables. So it's kind of an incomplete definition, at least in my mind. So we are kind of missing a rigorous transaction definition and implementation for an open lakehouse with the scope of the whole lakehouse. And that is what I mean about the mission towards a fully transactional lakehouse. So going back to the original question, what exactly is the isolation level of Apache Iceberg? Here is my personal opinion, a disclaimer. I think it is at the isolation of read committed snapshot isolation, which is shorthanded as RCSI. It is an isolation level similar to snapshot isolation, but from the sense of commit. However, you are not really starting a snapshot for the entire lakehouse. However, you are getting a snapshot of every single table when the table is first accessed, right? So that is really the definition of RCSI. So, but when we are talking about what would happen if you are running in that isolation level, it is read committed version of the snapshot isolation. So you will see phantom reads, you will see rescues, you will see rescues, all those kind of things. Here is an example of a rescue with RCSI, and this is actually even happening in a single statement transaction that is touching two tables. So here I have a join with T1 and T2, and within the join, you will first load T1 and then load T2 and then do a join, right? And things can happen between the two loads for whatever reason. Maybe it's a Java GC or something else. But if there's an insert happening to the second table, then you will actually see very awkward results. And this actually happens quite a lot when you have a dashboard and that's a complex join between 20 tables and different tables are being loaded at the same time. This actually happens. And I'm saying Iceberg is only kind of sort of RCSI because it is theoretically RCSI with a single statement transaction. But when it's used in a multi-statement transaction, it is, of course, read uncommitted because you can commit a statement in another process and you will see, and if you roll back that, the other process will see the dirty data, right? So it has dirty reads. And the actual isolation level really depends on the engine implementation. So for example, I think Trino actually does pretty great job in doing isolation guarantees for Iceberg, but for many engines, once you introduce the concepts like caching and time-based caching especially, then things get very complicated and you are really treating this as a read committed or read uncommitted system. So going back, a lakehouse with snapshot isolation, I think we should target to build that. And that goes into what our solution is as an overview. So what we are really trying to build here, actually. So here's a list of requirements that I gathered after I thought through all the motivations. So first of all, we want to support all the begin, commit, rollback, transaction SQL semantics. And ideally, we want to do the fancy distributed transaction thing. And we know it kind of really goes beyond Iceberg at this point, that we want to do multi-standard, multi-object transaction semantics. And we want to support at least snapshot and serializable to have very safe behavior and maybe other isolation levels if we can. So I guess it's some sort of transaction management framework, whatever that means, maybe a catalog and plugin. So we went through with this line of thought for some time, and then we gathered what the framework needs to do, which is the framework probably needs to track all the objects in the lakehouse, right? It needs to know what is in there, and it needs to describe to the callers what is the latest state of any object with the concept of the transaction, so that it is obeying the isolation levels. And it needs to manage all the activities against the objects. Because if you don't know the activities, then you don't know how to manage the transactions, right? That's pretty obvious. Unless the object is external, then it's kind of static. And you need to decide if some operations need to succeed and some need to fail in order to keep the isolation guarantees. So then we came to the realization that actually, isn't that just building a catalog? Because you can literally plug in catalog in this phrase and then everything still holds true. And it's not like a inclusion kind of thing. It's actually like the very basic thing that a catalog needs to do. So in the end, we basically build a custom catalog implementation that does all these. So the next question is, how do we build this catalog? I think we thought about it a lot of different ways, and the easy way is, I really like this meme, is that you can probably do that with a Postgres backend, and everything is solved, and Postgres keeps track of all the isolation guarantees. That is a pretty good design, I think. But this actually was a side project that I started, and there's no PM, there's no product. It's a pure research project. So I feel I can do something fun and something crazy about this. So here we go. What I was really interested in is S3 actually launched the feature of put if not match, which adds the atomic feature into the object storage. And that was the last thing that was able to make this possible, which is now almost all the major storage systems support some version of mutual exclusion of file creation, right? Because in most of the traditional file systems, you can do atomic rename in the Linux, in BetterFS, in HDFS. These can all do atomic renames. And for the commercial products, now we have all the 3 hyperscalers that are able to do put if not match. And even further, if you think about any other key value storage, you can treat that as a file system by using the key as the file path and the value as a blob. And that opens you to all sorts of storage systems like Postgres, Redis, Cassandra, HBase, and DynamoDB, right? So it would be cool, I felt, to do a catalog storage-only solution, right? And this is actually talked about quite a few times in the Iceberg community to say that here are a few references to our previous discussions, that if we could build a storage-only catalog, it should be able to depend on as few primitives as possible, and so that users can move from different providers if they want, and that, if supporting multi-table, multi-statement transaction, would be super cool, right? If we are trying to build a storage-only solution, that means probably that is a format, because a format is essentially a set of files in storage with a definition about how these files are related to each other, and a definition about the content of these files. If you think about Iceberg, Hoodie, or Parquet, all these formats, that is exactly what they are doing. So, okay, so in this case, now we are doing a catalog format, basically. It's a set of files in storage that defines the types of objects in the catalog, defines the actions that can be performed against different kind of objects. It defines the interactions between these objects. And we know it kind of has to be, we went back and forth about this. And right now it's outside Iceberg as a new project because we want to support things beyond Iceberg, but it will integrate back with Iceberg for sure. We'll talk about that for more afterwards. So this is a project we launched. We launched Olympia, which is what I call the open catalog format. And this is kind of the crazy, ambitious grand vision of that is you have the open catalog format in the middle, and below that you can have all the different standards, the different formats, and above that you can have different engine integrations. And now, from the vendor perspective, you are not really just choosing a single thing, that is what storage you want, right? And you can choose 1 or 2 or whatever number of things, and everything will build on top of that the whole stack is open source above the storage. And I call that a storage-only open lakehouse. So now that is the overview of the product. I like to talk about the architecture design as a deep dive. So this is actually the naive implementation we discussed on the Iceberg dev list. So we could potentially represent catalog as a single file on storage, right? A single file holding all the catalog objects with a key, which is catalog object name. The value is the definition of the object, and it has version-based naming so that you can commit just like you are committing a delta lake table or you are committing a length table, right? And if the commit if there are concurrent commits, then one of them are guaranteed to fail. And in this case, the naive implementation says that every time you do a new commit to the catalog, you will rewrite the whole file, right? Because it's a single file. And of course, this is not efficient at all. So we want to improve that in different ways. The first thing we came up with is that we want to probably use something to do faster lookup. So we did a B tree for that, which is pretty common choice at the data structure. So the B tree is stored as a single file, which each node is stored as a different pages in a file. But still, it doesn't solve the issue that you have to still rewrite the file every time. And if there are millions of objects, then that's not a good idea to do that. So what we did is we do instead of pages in a single file, we do one file per tree node. So in that case, you are really, if you are touching an object, then you are only touching the nodes that are related to that. And then the root node of the tree is really the one you are committing to the versions. And this also makes the whole system much more scalable because now you can store, I don't know how much the limit, but millions or billions of objects, and that will still hold the tree structure. And because B tree is self-balancing, so you are not really have to run any compactions on top of that. And so here is what we call the Olympia format overview. We are going into more details of that, about that in the later slides, but here it is really a B tree. You see there are namespaces in the B tree, and there are tables, and there are views in the B tree, and they point to different definitions that are stored either inside the tree or outside the tree. And there are different file types of the whole architecture. The first, most important file is node file. And we are using arrow IPC format because it's a columnar format for efficient access. And we are using the memory mapping to do zero copy access of the whole, all the node files. And each node file is a key value map. It's a kind of a sorted key value map. And it has 2 or 3 sections depending on it's a root node or it's not a root node. So for all the node files, it has system keys, which defines general information about the node, and it has the pivot table, which is really the representation of the tree about what are the keys to search and what are the child nodes pointers. And if it is a root node, there's a special section called the committed action that is used for conflict resolution. We will talk about later. So for the key in this B tree, for the system keys, which is the top section, if you remember, for all the nodes, there's the number of keys in the pivot table, and there's the node creation timestamp for information purpose. And for the root nodes, there are quite a few other things. There's a catalog definition, because catalog definition always needs to be accessed for reading anything. And there is a pointer to the previous root node, so you can do some cool things like time travel across the whole catalog. There's a rollback from root node in case you want to do a rollback, and there's a number of actions to access the action table. So for the object keys, which is the key to store all the different types of objects in the catalog, we have the prefix, which is the type ID of the object. It is a base 64 encoding, and then the name is padded with white space for lexicographical sorting. So here's an example. It's not supposed to be human readable of a key for namespace 1 table 1, which is like many equal signs and spaces. If you open the file. And for the node file locations, we kind of follow a mixture of like traditional storage layout plus optimizations for the object storage. So we have a version folder which stores all the versions, and the versions are stored in the reverse 64-bit binary. That is for optimized performance on the object storage, and thanks to all the learnings by doing the Iceberg object storage layout. But for simplicity, we'll just say the version number in the later slides so that it's more clear. And for the non-root nodes, it's stored in the node folder with just UID names. And we also have object action and definition files. Those are protobuf definitions, and the protobuf can either be stored directly as a value, or it can be pointers to a file if the payload is too big. And we call those files definition files. It's stored in the /def folder. And there are two very important files, which is the version file, the latest and oldest version. And the latest version is kind of similar to what Delta Lake and Lines does. It's the best effort ping to know what is the latest version of the catalog. And if there's no latest, then it's a 0. And the oldest is the guaranteed oldest version, because when you are doing things like catalog cleanup, then that raises the oldest value so that you are not accidentally holding a transaction for too long and committing to an old value, the old version that has already been recycled. So here, for when you are beginning a transaction, the first thing you do in the Olympia format is that you identify the latest catalog version. That you do by read the latest version number if it exists. And then starting from that number, you continue to seek for the newer version and check if it is greater than the oldest. And then you load the specific, after you determine the latest version, you load that into memory. There's a question about why not just listing that, which is what Delta Lake does. What we are trying to achieve here is we want to minimize the difference across the storage, if you remember the original purpose. However, lexicographical ordering is not guaranteed across storage. For example, here is an example of the S3 latest S3 Express directory bucket that does not return objects in lexicographical order. So we are not trying to depend on that. So we are only doing head object for that purpose. And that actually might be faster because list is not usually the fastest thing to do in a file system. And after you determine the latest version of the catalog, you will find the object in a B tree. That's a very standard B tree process. You go to the root node, you do a binary search of the key, you go to the node on the child, and until you find the value. And for updating the object in the B tree, we do a two-step process. The first step is you do the update in memory. So you first identify which is the node you want to insert the key. And here we give an example of the B tree that will be splitted after the insert. So it will be split. After the split, there will be information that is holding memory that is marked in red. And the green ones are pointers to existing node because the node is split, so you have the left part and the right part that will be still a part of a new node or some part of the existing node. So after everything is stored in memory, when you commit a transaction, by the way, you can do multiple steps, and the previous process will keep happening. That is how we do the transaction with multiple statements. And after you do the multiple statements, you will be able to commit a transaction. That is when you materialize all the things you have seen in green or red into actual nodes in the physical storage. And all the writes into non-root nodes can really happen in parallel because those are deterministic file locations. And after you write all the affected child nodes, you will commit the root node into the new version. For what happens to the concurrent transactions, there are two parts, the storage part and the lakehouse part. Because on the storage part, it is guarded by mutual exclusion of the file creation. So a very simple process, we try to commit two processes into the same location and one will fail, right? However, just like Iceberg does this kind of rebase reconciliation process, we are also having a similar process here, but in the scope of the whole lakehouse. That is the key difference here. So, and that is how the action section of the root node is used, because you are now comparing what happened in the new node versus what has been committed concurrently, and see if it can be recommitted by changing the new node in some version or the other. And after you change that, you will commit that to the next version, and the process of reconciliation on the storage and lakehouse repeats in case there are other concurrent transactions. So for the distributed transaction use case, now you can, because the whole design makes the catalog version, and the transaction is really just, you have a temporary B tree that is holding memory. So there is really nothing that is preventing us from materializing that B tree into the storage in some temporary location. And in this example, the Spark process is beginning the transaction and doing some work, and then it will save the distributed transaction into a location. And then the RAID process will catch, and the user or whatever process will tell the RAID that, okay, I have a temporary uncommitted transaction here, please pick it up. And then you can commit that into the final version to do the distributed transaction. And with this design, we actually realized there are quite a few new interesting features, such as you can do full catalog time travel. This is a very Very interesting feature that we see in systems like NASI, but NASI does that with branches and tags. And here we already have a linear history of the catalog, so you can time travel directly to some point of the catalog. And all the tables are very consistent at that point of time. Instead, you have to, in a single table time travel case, you have to realign the tables into the same point of time, which might not always be possible. And another benefit is really a portable catalog. We know we want to do relative paths in Iceberg, so we did that in this case. So all the path inside a Olympia format is relative, and you can copy that into S3, into GCS, into whatever storage, and you can have different copies, and they all work in the same time. And the same mechanism also works for snapshot exports, so you can export a snapshot into another location, and you can read that anytime you want. And it can be a shallow copy or a deep copy, depending on your use case.
Okay, so I'll be going over the integration with Apache Spark Iceberg connector. Well, multiple integrations, but here we'll start with the Apache Spark. So first and foremost, as you guys probably all have seen before, this is how you start a Spark SQL session with Iceberg. Just applying all the jars, the session extensions. However, with Olympia, we actually have our own jar that you need to supply, as well as some of the Olympia-specific logics, such as Olympia Spark extensions, and how to interact with Olympia with the Java catalog. And with that logic, you're actually able to get some of that traditional transaction sense with multi-table transactions in those SQL semantics. So you can run things such as begin, commit, and rollback transaction. And for the single table operations, these are treated as independent transactions. And you can imagine that every statement you make is wrapped with a begin and commit. So first of all, here we have a catalog from Drew that was initialized. And now we have another session that's going to be started for Jack. And in this case, all of the configurations are the same except for this isolation level. Here you supply an additional config of serializable, and we'll see why that's affected later. But in Drew's case, since he didn't set anything, he will have a default snapshot, or isolation level set to default, or snapshot. Okay. And we also have this scenario here where we will go into the analysis later, but I'll go over it at a high level. In one case, or in both cases, Drew and Jack are both talking to the same catalog. And here they both start a transaction. And we're going to treat these statements as acting in a line, or acting linearly. And Jack is going to start off by creating a view by selecting from T1. And afterwards, Drew will insert some values and commit. And next, Jack will also update T2 from the view in T1 and commit. And now in the analysis, we'll talk about why this is important. And here, actually, we're going to believe that the catalog is at version 99. And since Drew commits before Jack in that scenario, he is going to increment the version to 100. And that's going to leave an action of a table insert, T1. But for this scenario, Jack can't commit serially on top of version 100 because T1 has changed, and that would affect the results of T2. And in this case, there's another scenario that works. And if Jack actually committed before me, it would be a valid serial execution order. And in that case, we can see the conflict, and combine all the actions and increment the version to 100, or 101, and the previous route would be 99. Okay, so for the next integration, we're going to go over its integration with IRC via Apache Gravitino. And here you could see the infrastructure of what it means to integrate with the IRC, because if you're building a server for any communication protocol, for example, IRC, to integrate with engines, you can use the Olympia to fulfill most of those technical catalog interactions and focus mostly on the business layer. And since we're using Apache Gravitino, here's an overview. So Apache Gravitino is a federated metadata lake on top of the technical data catalog, and it performs data governance and enables open engine access for various data sources. Apache Gravitino IRC server follows the IRC spec and actually acts as an Iceberg REST catalog server. So in our example, we'll see how that works. But here you can see where Olympia fits into that architecture and Gravitino as a whole. So Gravitino offers some logic for monitoring, auditing, access control, and governance, and some additional logic for their APIs, such as the Jetty server, the routing logic, and some API translation logic to convert the Java code into the endpoints. And here you can see the Olympia Iceberg catalog. It's the special logic and how the catalog is expected to interact with our Olympia catalog. And now here are some configurations. And most importantly here, we need to tell Gravitino how to connect to our catalog. So we give it a custom catalog, and there's our implementation. And in the next slide, we'll see where we pass that in. So in order to run Olympia with the Gravitino, what we need to do is first download Gravitino, add some custom jars, such as the core and the S3 jars, and pass in the aforementioned configurations, and you could just start the server with this command. And yeah, this will be available later as a part of a link at the end. And so now you have this mythical Spark Iceberg Gravitino Olympia connector. And so now, since we have the server running, this is how you would be expected to connect to that REST catalog. And it's pretty simple. I think every catalog is ran like this now with the REST catalog implementations, and we just supply the type to be REST. But there is a problem with this, right? Because now we're not actually using the Olympia custom logic for multi-table, multi-statement transactions, and the IRC is actually missing some features, such as like the start transaction and passing that context around to be able to get that read consistency. So as a solution, we actually thought that we can leverage multi-level namespaces to represent transactions. And if we have this concept of distributed transactions, we can use this to share state across steps within transactions, right? And technically, we can hijack all of the namespace operations within Iceberg to simulate the multi-statement transactions, such as begin, commit, and rollback. And this is a diagram of how that looks. You have your catalog at the top level, and then you have this other directory that's tracking all of your distributed transactions with the transaction name and a copy or a snapshot of your catalogs in between. So now let's look at what it looks like to use those SQL semantics and interact with those distributed transactions. So first, we can create a database, and that's going to create the location for the distributed transactions. And we can use show transactions to show all the current distributed transactions that are going on against your catalog. Next, now how do we create the transaction? How do we create that catalog version, right? And we can use create database that calls the identifier for the multi-level namespace and pass in some additional properties to specify isolation level and start a transaction. And now with this, we can get that consistent read of our catalog. We can do things like show tables and get that state of the catalog, get our tables in that state, as well as select data from that distributed transaction and write data. And so all this is saved to storage, and eventually you're going to want to commit. And we can leverage the alter database to commit that transaction, as well as if you want to do a rollback, save some storage, you can just drop that transaction. Okay, so now we're going to go over a few slides for the next steps. And first and foremost, we have some fundamental next steps. We'd like to finish out a few key features. We can do things like add the conflict resolution, delete markers like tombstones to make time travel a little more easier, as well as rollback logic. And also, we'd like to refine and release the initial Olympia catalog format spec. And we'd also want to move from Java, everything's in Java right now, we'd move to a more robust language like Rust and introduce some cross-language bindings. And I also think one thing that's really cool here for the storage primitives would be to integrate with Apache OpenDAL or Apache OpenDAL for generic storage access. Also, one thing is the B tree gets better, right? There's other optimizations that can be done for our use case, and we can evaluate the performance by tuning that B tree and improving the design. And lastly, we would like to improve the auth-z experience and define how DCLs work in a transaction. In terms of integration, we'd like to support more table formats. Like Jack said, that this kind of goes beyond Iceberg. We can do things like integrate with table formats such as Apache Hudi, Apache Pymon, Delta Lake, and Lance. We'd also like to support more object standards, such as the substrate view, the Apache data sketch index, Apache calcite functions, and Cedar policy. And we can actually go beyond Spark here, right? We can do more engine integration, such as Trino, Apache Flink, Ray, DuckDB, et cetera. And lastly, support more communication protocol integrations. HMS, Lance catalog would be nice, MCP, et cetera. Okay, so for the last slide on next steps, we have the Apache Iceberg REST catalog changes that we'd like to introduce. And we'd like to, one of the issues we ran into earlier, as you saw, that led to us using the multi-level namespace stuff was the lack of begin transaction, rollback transaction in the REST catalog. If we can introduce those, we can be able to have the context to know we're trying to read against a consistent state and have all API calls handle that. And to learn more details, here are a few links. There's a GitHub link, the Docker image from earlier, some documentation, and yeah, please join Slack. And after all, this started out as a fun side project, a lot of whiteboarding, and yeah, we'd love to keep iterating and continue research with you. Thank you.
Sure.
Yeah.
Grab one for the audience. And can you repeat the questions as for the, here you go.
Hey, thanks, guys, for giving an overview of that. I have a few questions.
Can you turn on the mic? Maybe it's not turned on.
How about
Okay,
now?
okay.
Yes. So I was wondering, like, why all of this is not possible with IRC. Like, in my mind, like, all we are missing is a logical clock for the catalog. And if you provide, let's say, begin could be represented as a load table, or you can provide a load table with as of semantics, and that covers up all the isolation kind of mismatches. And like, why do we need another catalog implementation that still has to be like a plugin SDK and not something that could be behind a REST interface?
I see. I don't know if I could summarize right, but it seems like the question is, why do we need another solution? And we already have IRC. Is that a short summary?
In the sense that the problems that you described, I think they will be easily fixed within the IRC, rather than having yet another solution.
Yeah, so it can be easily fixed by IRC, not in yet another solution. Yeah, I think we are in total alignment here because, as we said in the last slide, we probably just need a few more concepts in IRC and things can work. But IRC is a protocol, right? It's a standard. And there are different implementations like Polaris, Gravitino, all those kind of things. And this is really, to us, more research about how we can do that in storage only. I think that is the main exploration we were doing. Yeah.
Anyone else?
Yeah, so I think that Iceberg's snapshot isolation works really, really well for like kind of keeping the scope of a transaction or a commit really small. So for example, like if you have like a streaming ingestion table, like you can write to that table tons and not really worry about a lot of conflict, right? Because you generally only have like one application that's doing the streaming ingestion into that one table, right? But now, if you have these catalog-wide transactions, you might have hundreds of tables that you're streaming into, right, with many, many writes per second. Like, do you guys, have you tried to see what that kind of looks like in terms of being able to apply all of these catalog level transactions with so many potentially conflicting writes happening simultaneously?
I see. So I guess the summary of the question is, in stream use cases, there are tons of commits going into a table at the same time. And if you think about doing that for many tables in the same catalog, then how does that look like in the solution we are proposing? So, and that's actually an amazing question, because we didn't, we trimmed out those slides because the talk was going too long with 90 slides. I think this is really almost a question about discrete mathematics versus continuous, right? Because the transaction is, in my mind, fundamentally the other side of the coin of streaming, because in transaction you want to see events happening in a discrete manner into the lakehouse. However, on the streaming side, the stream is really the great word, right, to describe the situation. That is a stream of events coming to a table. It is almost, you want that to be continuous, not in discrete chunks. It's just the technical limitations are making that into discrete small chunks. And the framework here really kind of forces us to think how these two different sides of the coin should be reconciled with each other. And this is a very open question. I don't really have the solution right now. Currently, my thinking is that the streaming use cases can happen independently into different transactions. And the transaction really should be fitted more into the business need, that you want the business side to see that these are like, it's almost a ledger, right? You want to see that these things are happening to these tables or these objects at the same time. So I think there could be a process where the streaming is streamed into isolated versions of the catalog into different tables, and those are not really conflicting with each other. And then you reconcile those as completed transactions into the catalog for business purposes or ledger purposes. However, on the other side, when you are consuming that in the engine, you can consume the specific version of the lakehouse that is having those streaming tables enabled, but you don't really have to increment the version of the whole catalog for that purpose. So that is my current thinking, but it's very open question right now. As I said, it's a research almost. So more discussions are needed. Yeah.
Okay, we have time for one more question.
So I was wondering, the design that you showed, how extensible it is to nested transactions. And the scenario that I'm thinking about is you begin an outer transaction, you start doing some work, and you have multiple inner transactions. And then like in case like you want to roll back, you have to roll back multiple inner transactions and the outer transactions. So this design, do you think is extensible to that, supporting that kind of scenarios?
Yeah, that's actually another thing, because I know there's like nested transaction in Postgres, for example, and this is able to support that. And when we were doing the distributed transaction, actually the original design was saying like you can do that, but we kind of removed that because it's getting not very too complicated, but you really want, right now the distributed transaction is just stored directly as a file, and if you update the transaction, then you are directly overriding the file. There is no atomic guarantee there, but there is nothing really stopping us from also adding atomic guarantee into updating that distributed transaction. Then you can really go recursive then, because you can just keep recursing and opening sub transactions. Although I'm not recommending that, but that is possible, yeah, for sure.
Hello? Great. Thank you so much. Thanks for the session. And remember to rate the talk on the app.